Okay.
Okay, there we go. Okay, all right.
Yep. Okay. So let's talk a little bit more about railway gauge. It really started with mine tramways in the UK, basically in the 17th and 18th centuries. And they were based around horse-pulled carts on wooden rails and later iron rails, such as this. And the rails were basically ideally spaced for a horse. So if you can think of the leads of a horse, the rails were spaced so that the horse could walk in between the two rails. And then that carried on. Oops. Let me see if I can. There. That carried on to the introduction of steam engines and then modern diesel engines. And so basically the gauge is based on what was used in coal mines in the 17th and 18th centuries. Let's talk about why we have such a strange measurement for gauge. 4 feet 8.5 inches is the measurement. How do we come about that? Well, nobody's really quite sure, but what it appears to be is the early railways used what was called plate rail. So this basically flange or L girder, and they measured basically from the outside here. So 5 feet from the outside of one plate rail to the other. So on the left of your screen, you see the original plate railways. They went out relatively quickly because that plate rail tended to break very rapidly. It wasn't that strong. So then in the early part of the 19th century, we went to what's called T-rail, and you see a few examples of early T-rail, basically in the UK. And then today, on the far right, you see a drawing showing the wheels and rail, as well as a close-up of the wheel rail interface. But basically, the measurement now is 4 feet 8.5 inches, which is the inside of the wheel as opposed to the outside, which seems to explain why we have such a strange measurement today for standard gauge. By the way, other gauges typically use even numbers. So at one time, there was a lot of narrow gauge in North America, and it was all 3-foot gauge. Or the British colonial gauge was 3 feet 6 inches.
Oh, the moose is out there, but outside the fence.
So it's only standard gauge that has
You
such
can
a
see it
strange
from up
measurement.
here.
Unfortunately, trains can make the news in ways we don't really want if you're a railroader. You may have heard last year about a big derailment in East Palestine, Ohio, that became a very major political incident.
Okay.
From a railroad point of view, this was a very benign incident. There was nobody hurt, nobody injured. When the derailment originally happened, all the cars and equipment remained on railroad property, didn't hurt any third parties. The picture here shows it after the track was relayed and the cars were moved off the railway's property. And all the cars remained intact. There was no release in the original derailment. So from a railroad point of view, this is a very benign incident. It's big, but really it was very good. It became a huge political issue, though, because emergency services decided they're going to blow up a couple of the cars. And when that happened, it released vinyl chloride. And the vinyl chloride went through the town, and then it became a huge political issue. If you remember, Donald Trump made a journey through there, and then it became a big issue with the Democrats and the Republicans. And to date, the railroad that occurred on has spent $1 billion in cleaning up this what should be a relatively minor incident, but they've spent $1 billion. So it's enormous. And there's all kinds of political agendas come out. And as a railroader, it just drives me crazy. So for instance, one of the big things that came out is all kinds of people saying, well, your brake system is 150 years old and you need to update your technology. Well, that's not true. And the brake system wasn't the cause and wouldn't have changed anything. The derailment happened because of a failed wheel bearing, what railroaders call hot boxes, and I'll talk a little bit about that. The hot box is a problem for railroads, and we're always working on technology to try and prevent these kind of derailments. It is quite a concern, but it's proven a tough nut to crack. And I'll talk a little bit about brake technology because some of the things they're advocating just don't make sense. So, hot bearings or bad bearings. Hot box detectors are used to find bearing failures. And basically what happens is most of the hot box detectors will read the temperature of every bearing of every car going by on both sides of the train and compare it to the ambient temperature. And if it exceeds a certain threshold above the ambient temperature, there will be a warning goes out to the train crew and to a central office. And depending on the temperature, the train crew will be required to stop immediately, check the car, and set it out, go at restricted speed and set it out at the first available siding or backtrack where you can set it out and get it out of the way. In Canada, the hot box detectors are placed every 35 miles, and they're placed before every city. So, for instance, in Calgary, there's a hot box detector just east and just west of the city. So you can try and prevent derailments anywhere around a populated area to the best of your ability. The problem with the roller bearings that they use, though, is that often you don't get very much warning. Oftentimes they will fail like that before they heat up. And as they do heat up sometimes, and the East Palestine bearing was a situation like this, the bearing was heating up slowly. So it went past 3 or 4 detectors and was getting hotter and hotter and hotter, but hadn't reached the threshold for reporting when it went by. So there's another type of technology that we started to try about 20 years ago to detect what we call screamers in the railroad industry. The railroad industry uses a lot of very basic language. But bearings, when the theory was when bearings start to fail, they make an inaudible sound that you can detect. And the idea was, or the theory was, you often are able to detect the screamers a couple of thousand miles before they're actually going to fail. And that allows you to do some planned maintenance then and get the car into a shop and get the bearing fixed before it fails. The problem is the screamers didn't work all that reliably. So we still need more work on that. The other thing we probably need is more work on AI to detect hot box detectors that go through multiple scanners, don't reach the threshold, but are gradually going up. Now, if you can think of a person trying to follow that, you got a train with maybe 600 axles, and following kind of small changes in ambient temperature over the course of 2 or 3 detectors, it's impossible to do as a human. But with AI, we might be able to detect more of the trend and capture more of these.
What's the life cycle of the roller bearing?
Well, the average roller bearing will go for the life of the car without any failure. The last time I checked, and this was with older technology, we were averaging well in excess of 1 million miles, car miles between bearing failures. So they are incredibly reliable, but you know, anything mechanical on the outside, you're going to have problems. But yeah. So now we got to talk about brakes, because one of the things politically, everybody started talking about brakes after that East Palestine derailment.
But there's one here.
So railroad brakes, the basic concept
It
of
like
railroad brakes
that
used in
tree.
North America was set by Westinghouse in 1869. And we still use the same control and power signals. So basically what happens, and I'm just going to go up to the screen here, and I don't think my cursor, oh, is my cursor showing up? No. Basically, the way the brakes work is you pressurize the train line, which is this line here, at about 90 to 110 psi before the train can go anywhere. And you got to test before the train can leave its initial terminal. You test to make sure your getting flow all the way through and the proper pressure at the end of the train. That pressure charges reservoirs, auxiliary reservoir and emergency reservoir. And there's a control valve or a triple valve here that basically will apply the brakes when the pressure drops. So the basic concept is the brakes are off at say 100 PSI, but if you make a 5-pound reduction, the brakes will start to apply. And if you make a very rapid reduction, that's say 15 or 20-pound reduction very rapidly, that will invoke the emergency reservoir, which will give you even more braking force. And so that applies the power to brake the train, brake the cars in the train. So these systems have been updated continuously, including this year. They just issued a new controlled valve design. But the control signal, dropping the air to put the brakes on and increasing the air pressure to release the brakes, hasn't changed since 1869. So that's the thing that's the backward compatibility that we still use. But everything else in brakes has changed since then. What a lot of people in governments are proposing is what's called electro-pneumatic brakes. And this would be a combination of electrical control with pneumatic brakes as well. The problem with this system is it's not backward compatible. So to make it work, you need every car in a train to be the same brake system. You have one car that isn't, now you got a problem, particularly if it's the first car behind the locomotives. The other problem is it's horribly, horribly complex. So now you got to run, say, an electric circuit through 2 wires through up to 200 cars in a train. And it's all got to work perfectly reliably, because if it doesn't work, you're not going anywhere. And trying to get everything to work in our climate, particularly, 30 below, it's a challenge. So the lack of backward compatibility and the complexity and the cost and the idea of trying to change literally 1 million cars is staggering. The railroad industry is not real keen on that, but the railroad industry has a bit of a different idea. One of the reasons for electro-pneumatic brakes is the control signal propagates through the train in the airline at the speed of sound, whereas an electric wire would propagate the signal at the speed of light. And so the feeling is being able to apply the brakes all the way through a long train at the speed of light will improve your brake handling. And it will do that. But there's a different way to do that I'll talk about in a few minutes.
What is the expected time
What's that?
when the train is not moving? How's that?
Well, there's 2 things. One is when you first stop on air, the cylinders will hold the brakes for a minimum of 3 hours. They'll usually hold quite a bit longer than that, but we will only allow it to be held for 3 hours. After that, you go to apply handbrakes. There's handbrakes on every car that you've got to apply. Yeah.
Is that what happened in Lac-Mégantic?
Well, yeah. In Lac-Mégantic, there was a couple of things that went wrong. So basically, they stopped the train on a grade at the top of a hill. The engineman applied the air brakes, but the air bled off over time. As I mentioned, you couldn't count on it more than 3 hours. Well, in the middle of the night, enough air bled off that the air in the cylinders wasn't holding the train anymore. He also applied the separate engine brakes. They're called an independent brake. And they were holding the train. Plus he put handbrakes on a few cars. So what went wrong? The engine started on fire in the middle of the night when
you got pictures here.
was asleep. Emergency services came out and pressed the emergency stop button on the engine. When the emergency stop button stopped the engine, it stopped filling the air for the engine brakes. And what he was supposed to do, what you're supposed to do when you set handbrakes is you do what's called a pull test. So you put on the handbrakes and then you use the unit to pull the train and you see if it moves or not.
Yeah.
If it doesn't move, you got enough handbrakes set. If it does move, you got to set more handbrakes.
Like, I'm not going
He
there.
didn't do a pull test. He just put a few handbrakes on and left. So there's a whole bunch of things went wrong in Lac
Oh,
Mégantic,
I turned back actually.
and the railroad industry is still feeling the effects of that. Let me tell you. Yeah, that was a bad one.
The baby had on TV in the
What, I'm
morning.
sorry?
If you're coming out of hibernation.
Yes,
Basically,
yes.
has that
big,
much
huge
ice
problem.
and it's breaking
And there
through
were,
like snowpack.
the
And then
Quebec
the head
provincial
pops
police
out.
were looking at criminal charges. I don't think they applied in the end, but they were looking at criminal charges on some of those people. Okay, so let's move on to locomotives a little bit. Canadian conditions led to new motor and control technology. So traditionally, locomotives in North America are diesel-electric locomotives. Just transferring the power hydraulically or mechanically to the trucks just doesn't work. There's too much horsepower. So the diesel drives a generator, and then you have electric motors hung on every axle. Traditionally, we've used DC motors because the DC motors are relatively easy to control for speed. But there's some real problems with DC motors, particularly in Canada. The air intake, before I go on, the motors heat up quite a bit, and you got to blow air on the motors to keep them cool. In Canada, we have a lot of dry blowing snow. So the air intake in the locomotives would blow snow on these hot motors, cause all kinds of moisture, and short out the motors. So every winter, we had all kinds of locomotives in the shop having to replace the motors. And that was a major effort every winter. To solve that, you could go to AC motors. The other problem, by the way, with DC motors is they have a short time rating. So you can burn them out very easily if you apply full power for more than a short period of time. And if you can imagine starting a train on a steep grade, you may be a half hour or more before you can get to the top of the grade. You could burn out all the motors in your locomotives. What's that? Yeah. It's you just burn everything out. So CP pioneered the use of high horsepower AC motors in North America in a conventional MLW unit, so Montreal Locomotive Works unit. This was possible because of advances in high energy semiconductors, which allowed variable speed control with AC motors. I think it's thrice sisters technology that was required. Today, that started about 30 years ago almost. Today, almost every locomotive in North America is running on AC motors because they've proven so efficient and so effective. There's many other advantages to AC motors, such as dynamic brake efficiency, which I'll talk about in a minute as well. So dynamic brakes, basically what they are is another brake in a train, and the motors hung on every axle, you reverse the wiring, turn them into generators, and then the electricity generated on these motors is wasted as heat at the top of the unit. Almost every locomotive today is built with dynamic brakes. The heat is basically wasted, and there's large fans in the top of the unit to blow over the resistors because there's a lot of energy generated. The AC motors are far more efficient than DC motors at dynamic braking. And so what happens is today, the locomotive engineers are restricted in how much dynamic braking they can apply because they can actually cause some very serious forces in a train that could derail a train if they apply too much dynamic brake. You couldn't do that with DC motors, though. This provides a really key additional brake system for trains, in addition to the class brakes on the cars. Another bit of interesting technology is the robots. So basically, you've probably seen trains with locomotives spaced in the middle of a train or several places in a train. That started in North America. Basically, it was CP perfected that technology in the late 60s. And it came out of NASA with telemetry technology for spacecraft. So what happened is the telemetry allows a lead locomotive to control a mid-train locomotive. And at first, when the technology came out, we were using first generation equipment, which is a lot of tubes, required a lot of power. So you had a diesel generator and a separate car with this big radio system and then a control system that sent the controls to the remote locomotives like you see here. So this is what we used to call a robot car. Today, we're on third and fourth generation technology, and it fits in a very small package in the nose of a unit now. So we don't use robot cars anymore. But the current technology, which has been around for about a decade, has been advanced. When it first came out, you could have one set of remote locomotives. Now you can have remote locomotives in about 5 different locations in a train. And this has really helped us change the in-train forces. The trains are so heavy now that the forces are just immense, and it can cause big issues unless you manage it properly. So when we talk about remote unit or distributed power, basically what happens is we're changing the forces. And I'm just going to go to the screen again. At the top here, you see a conventional train, and the drawbar force is increasing as it gets near the locomotives. And the forces can be quite something. Couplers have to be designed for 1 million pounds. And, you know, a coupler is relatively small, so that's quite a force it's got to withstand. And you can stringline trains to derail a train around a curve because the force is so high. So by putting mid-train power, our drawbar force goes down. So in this example, we have 3 units, a head, mid, and rear unit. And you can see the drawbar force is dramatically reduced. The other thing that's happening is the brakes. Remember I mentioned the brakes? The railroad industry has a real problem with electro-pneumatic brakes. But with remote units, you can send the brake signal to the remote locomotives, and you're getting the effect of the speed of light to the remote locomotive. Now, it will propagate through the cars nearest to it at the speed of sound. So it's a combination of the speed of sound and the speed of light, but much faster than propagating the brake signal from the units just at the head end alone. And that massively improves the brake response.
With strain gauges and all measuring the power, I need to balance the load between the locomotives. I mean, it's quite a complicated algorithm.
Yes, it is. And we have a bunch of physicists that used to work out all kinds of plans for us on the trains and how you could configure trains. And we literally had a small crew of physicists. I used to work with one of our physicists.
They do have strain gauges measuring them.
We use basically simulations most of the time. We have pretty good simulator systems that can calculate all this within a reasonable range. And it's called the Davis formulas, which are well known in the industry. But anyway, these multiple locomotives in the train have allowed us to make much longer trains. So now we can run trains up to 18,000 feet long, or well over 3 miles. This reduces the number of trains, which in turn increases track capacity. So we get a lot more capacity to move traffic without double tracking. Now, sorry. Yeah, the question for the remote people is how long does it take for a train to pass? It can take quite a while. At 60 miles an hour, it's not too bad. But, if you're entering a yard at 10 miles an hour, it can take a long time. That can be an issue. So some people were asking about the Mount McDonald Tunnel. So in the 80s, we were having a capacity problem in Rogers Pass between Golden and Revelstoke. And to solve that, we built an approximately 9-mile long tunnel, the Mount McDonald Tunnel, under Rogers Pass. The engineers always used to say the greatest challenge in that tunnel was the ventilation system. By the way, I used to have to give public presentations to farm groups and all that while it was under construction. And the question I always got is what happens if they don't connect in the middle? And the answer was, well, they just keep on going and we get a second tunnel for free. But one amazing thing I will say is the east end, they used a tunnel boring machine. And they had a laser to line up the tunnel boring machine, but they had to compensate for the effect of gravity on light. It was that long. So I thought that was rather amazing. Anyway, the ventilation system was the biggest challenge for building the tunnel. Let me just give you a quick description. Again, I'm going to go to the screen. So a train enters the east end through a gate. The ventilation system at the top of a shaft here blows air over the train through here. There's a gate closed in the middle. As the train goes through here, that gate opens and air from the west portal is drawn in and up the shaft. So the shaft is divided in half, while the other half of the shaft is blowing air out that way. And then the gate closes and the train carries on. To give you an idea of how much air is involved, the fans require 12,000 horsepower. Yeah, it's like being in a small hurricane inside, and they had to reduce the grade in the tunnel. So the grade out on the approach to the tunnel is 1%. Once you're in the tunnel, the grade had to be reduced to 0.7% because of the air resistance from the wind blowing over it. Now, I always thought, for 20 years, I thought that the ventilation system was to remove exhaust gases. In fact, the design was not for exhaust gases from the units. The design was because of concern of permanently heating the rock in the tunnel to the point where the units would die from being too hot inside the tunnel. And there was a great amount of work done when the tunnel was designed, looking at the heat released and building up in the rock. I mean, if you've been in the tube in London in the winter, a lot of those tube tunnels are hot even in the winter, and that's from 100+ years of resistance building up in the tunnel. And the same thing happens here. So when I was working in our capacity group, we were concerned about getting to the limit where we couldn't get enough cool air in the tunnel. By the way, just a little anecdote. I was on our track evaluation car going through the tunnel one winter, and it was 30 below outside. We have a thermometer on the car, an exterior thermometer. It was 30 below when we entered the west portal. Within 5 minutes, it was 70 degrees Fahrenheit. And basically that's from the rock in that tunnel. So this temperature is going to increase over time, and electrification may be required in the future. In fact, the tunnel was designed high enough so that you could string a wire in the future. But stringing a wire is extraordinarily expensive. So we looked at other options. And why don't we basically generate electricity from grain rolling downhill instead of water flowing downhill? Some 70+% of our tonnage is westbound to the coast, dropping at least 3,500 feet. Some traffic like coal, which amounts to about 6 or 7 trains a day, drops from 5,600 feet. So an even steeper decline. So the idea was, can we generate enough electricity from the drop to power trains the rest of the time? And the answer was, with AC motors and dynamic brakes, we might actually have surplus power, surplus energy, just from rolling grain and potash and everything else downhill. The problem is the battery and supercapacitor technology is not there yet. The batteries are getting a lot better, but there's a couple of problems with batteries. If you look at this old profile, you see a very steep, relatively short downgrade. If you're applying the dynamic brakes on that downgrade, there's a huge amount of energy has got to be stored very quickly. And the lithium ion batteries are somewhat limited, too limited to store all the energy that would come out of the dynamic brakes. Supercapacitors could handle it, but supercapacitors don't have the energy density yet. So we need to kind of combine supercapacitor technology and battery technology. And apparently there's research going on that to try and get a synergy that will work in the long haul. But that could be a major advance, and of course does a lot for greenhouse gas emissions. So that's not the only thing. CP also has a hybrid locomotive. And this is powered by a Ballard fuel cells and hydrogen. So there's one been in service for about a year or two, and there's a few more being modified right now for use in hydrogen in Alberta as test beds. These are the first ones in North America. Basically, I'm sorry, GE is the one, I got ahead of myself. GE is working on a hybrid locomotive with batteries. And they have about 20 that they've got ordered right now. There's 2 or 3 in use and about another 17, 18 on order. The problem is with the batteries they have right now, they only get about 30 minutes at full throttle. So that just doesn't cut it for, say, going upgrade in Canada. But when you have the other green option, which is the, I'm sorry, I got ahead of myself with the hydrogen units. So we've got one operating around Calgary right now and a couple more being modified for hydrogen. Hydrogen gets a lot of political kind of check marks and kudos because there's no particulate matter and no greenhouse gases coming out of the locomotive. But there is a problem. Most of the hydrogen we have in Canada, and certainly in Alberta, is produced by steam methane reforming in Fort Saskatchewan, which produces a whole lot of CO2. So it isn't really net all that green yet. Now, the green lobby is saying, well, you know, we'll get to the point with renewable electricity that will do electrolysis to create hydrogen, but we're not there yet. And so, you know, the hydrogen powered locomotive, you know, it's interesting, but I'm not sure it's going to be the long run answer unless we can find a way to mine hydrogen. What's that? You know, that's one of the test questions. It cannot store enough to say, be like diesel and go to the coast. These units are restricted to operating around Calgary so they can be refueled. Okay, a little bit on track. One of the things that may interest anybody interested in technology is our track evaluation car. So we have 2 trains that go across the country constantly. They're about 3 or 4 cars long. The rear car has about 32 processors on it and a whole bunch of sensors. And it will basically every foot take a measurement of the track geometry and the rail, measure the rail for wear. It will have a camera with an AI system that will check for joint bars to make sure there's no breaks in joint bars. And there's a car with a split axle that puts pressure out on the rail that can test for tie condition. It can inspect up to 60 miles an hour without a problem. And it's rather amazing. I did quite a bit of traveling when I was working on this car. If there's a couple of different categories of defects. So the government has a whole bunch of standards, and this car measures against those standards, but CP holds itself to a higher standard. So if you have something that meets the federal government standard, but does not meet the CP standard, you'll get a priority warning. And this will go to the roadmaster who's in charge of track maintenance for that section of track. And if you have an occurrence that doesn't meet the federal government standard, now you got a bigger problem. And there's sirens go off and lights flash and it says, warning, warning, you know, urgent defect. And basically what you got to do is get on the radio immediately to the dispatcher and put on what's called a slow order. So you got to get the trains to slow down to an acceptable speed for whatever that condition is. And the track conditions are measured in 10, 25, 40, 60, and 80 mile an hour speeds. So most of our main line is maintained for class 4, which is 60 miles an hour. If you don't meet that standard, you knock it down to 40. If you don't meet that standard, you knock it down to 25 and then down to 10. And basically the track people ride on that car, the guys who are actually maintaining the track, ride on that car, and when your run is finished, they're given a book like that high with all the readouts of their track, with measurements every foot and every exception that's monitored, and they've got to be on that right away to correct any of those defects. It's quite something, and the processing power on there is really quite amazing.
So, Paul, given you only have 2 such trains, how often does a piece of track get managed?
Well, the main line west of here is at least 7 times a year. A branch line that only gets 1 train a week, maybe once every 3 or 4 years. So it varies depending on how much tonnage there is on a line. It's worked out. But you're west of here, you're looking at every 2 months, basically. And the other thing that goes on, they keep records of all these inspections, and you can basically do all kinds of calculations on the change from one inspection to the next. So if you see a particular recurring problem, you may have a bigger problem than you initially think, and can put more resources at it. I'm sorry, how often do you have? It can vary. So on one of the trips I did from here to Edmonton, it went twice. You tend to get the worst of it in the spring when the thaw is occurring, because the sub-road bed is starting to soften up. In the winter, you don't get too much because everything's frozen and it's stiff. So as long as you went into the winter in good condition, it should stay good most of the winter. But starting, say, March through to May, you will get more as the subgrade starts to soften. Yeah.
So, like, what's sort of major overhaul on the highway, all kinds of drilling of pipelines that are that rail, and we can answer the they monitor the rail, sure that.
Yeah, the answer is yes and no. Anything that's done on our property, you'll probably have a roadmaster go and inspect it, make sure, and he'll do a visual inspection. But he'll probably have to wait to get this more measured inspection the next pass of the track evaluation car. One of the things I forgot to mention, the track evaluation car is weighted like a freight car. So it's weighted at about 140 tons. So the track will move under that more than it would if you're just looking at it, which is, yeah, it's one of the key reasons why we do this. So that's quite a big part of our track safety program, is to make sure we're doing this monitoring on a regular basis. Next keen thing is top of rail lubrication. Sounds pretty crazy. For 60 plus years, we've been lubricating what's called the gauge face. So the flange of a wheel on a curve will rub against the rail. And so we've been lubricating curves for a long time to reduce the friction of the flange on the inside of the rail. About 20 years ago, they discovered that top of rail lubrication will not only reduce friction on the top of the rail, but will increase the tractive effort of the units. Now, you'd think if you're putting grease on the top of rail, your units are going to slip. It actually improves the traction. It's the wildest thing, but it reduces the friction on the following cars. Kind of improves, sometimes you can have your cake and eat it too. The top of rail lubrication was a huge advance. We're getting 5 to 10% fuel reduction from top of rail lubrication. That's huge. Yeah.
The same grease on the top of rail that you used on the flange face?
No, one of the things that's changed over time, well, I should say that we are using the same basic idea, but because of environmental concerns, the lubricants we're using now are often vegetable based. They may be modified with some other chemicals, but you want it to biodegrade as it's spread along. You don't want it to be accumulating and cause an environmental problem. The old gauge face was just petroleum-based lubricants, and you have this black streak along the track around the curves, which did cause environmental issues. We don't do as much gauge face lubrication as we used to. It's mainly top of rail now. What's that? The gauge face or the top of rail? There's a couple of, this system is a trackside system. And there's basically pressure bars. You can see it just squirts a little bit of lubricant just ahead of the wheel as the train goes by. There's another system. There's a couple of other systems. There's some that are locomotive mounted, some that are truck mounted. You've probably seen high rail trucks going along the track. Sometimes we have the top of rail lubricators mounted on these pickup trucks when say a track inspector is doing his inspection. But most of the time now it's these wayside systems. And one question we always get is welded rail. So in the old days, we used a lot of jointed rail, and basically there was always a gap between two rails. The rails were typically 40 feet long. And in the summer, that gap would close up as the rails expanded. In the winter, the gap would expand as the rails contracted. And the problem is the gaps are very problematic. There's a lot of wear, a lot of maintenance, a lot of concerns anytime you have jointed rails. So basically now on any major line, we have welded rail. But the rail is up to 10 miles long without a break. So the question we're always getting is, how do you deal with the expansion and contraction? Well, the answer is rail anchors. So I've got basically a picture. This is a rail anchor just outside of the rail, and there's a hammer there that's going to knock it on. You can see this picture. The rail anchor flips around the rail at the tie. Normally what we do is box a tie with an anchor on each side, and we box typically every second tie. It varies depending on where you are, but typically every second tie you box with rail anchors, and that will hold welded rail in place, and it will force the expansion and contraction into the cross section of the rail. Well, yeah, the rail has to be laid at a very specific temperature, because what there's two problems you can have. One is, in very cold times, the rail can break apart. It'll just contract and break. The other thing you can have is what's called a sun kink, where the rail pushes out from the ballast, and you have a big kink that will derail a train. So to prevent that, now the ballast has to be 18 inches outside of every tie to hold it in from sun kinks. But even that, when it gets very, very hot, will typically slow trains down. But we lay the rail basically hot at a specified temperature. The engineers have different standards that they use. And the idea is that you want to make the probability of a pull apart far more likely than the probability of a kink. The reason is the signal system will protect you from a pull apart. The signal system needs a completed circuit to be clear. If you have a rail break, the signals will drop to red. So we get protection from a broken rail, but we don't get protection from a kink. So that's why we like, yes, they'll have basically rope with basically soaked in a petroleum product that they run along the rail. They light it on fire and it'll heat the rail up. What's that? You can to a certain point, but most of the time they're using heat. And they have I've been out with roadmasters when they're measuring, they have a thermometer and they're always measuring the temperature of the rail. You'd be surprised. Like in one inspection I did in South Dakota, it was hot. It was like 110 Fahrenheit. But the rail was 160 Fahrenheit. Boy, I'll tell you, it gets hot in the sun. So, oh, sorry.
I thought I'd seen some rails that does not be sliced in lengthways.
Yes. Yes, you can have that. There's a couple of reasons you might do that. One is a derail, where you derail a train purposely. So in some cases, if you have a yard, you have the derail set to derail. So if any cars run out, they will derail rather than going down the main line inadvertently. We have the split switch where you have the thin piece, and we also use that angle at things like swing bridges, where you have some very complex joints at swing bridges that then open up, and so the bridge can swing or move. They're pretty rare, but you don't want to do them if you don't have to, but you do have them. Now, you've probably all heard of fail-safe design, particularly with the nuclear program. Bet you didn't know it started with the railroad industry. So fail-safe design started with signal and brake systems, and the concepts originated in the UK in the 1880s. Design principles were pretty much formalized by 1900, and I want to just give you one illustration. Modern signal circuits with fail-safe design and integrated circuits, well, you can't really look at it unless you got a microscope. And even then, it's pretty hard to understand. But let's look at an older mechanical system using semaphores. These are still in operation in the UK. They still work. Yeah. So these signals are all at their most restrictive position. To be less restrictive, they go down. They're called lower quadrant signals. So they go down like that. Here's the safety problem. If by some reason the mechanical linkage broke, the signal would fall by gravity and clear. Big problem. So here's what, you see these extensions down here? Those are counterweights. So if the mechanical linkage fails for any reason, the counterweight will keep the signal at its most restrictive location. You do the same thing electrically and there's all kinds of the signal engineers go wild with all this design criteria. But it's really ingrained in signal engineers, the whole idea of fail-safe. It's really quite something. So that's basically what I had. Hopefully I didn't bore everybody, but there's some interesting stuff to me anyway. So yeah.
Hold on, right.
Yeah.
Sorry, I was just saying, it's quite surprising. I never realized there was much engineering technology involved in that.
Oh, there's a lot. And I've just scratched the surface, really. There, yeah.
So, Paul, there have been several proposals in Alberta, high-speed rail to Edmonton,
Yes.
the new one from airport to Banff,
Yep.
Hyperloop from here to Edmonton.
Yep.
Can you speak to these? Are any of these gonna happen or? What?
Okay. I worked on one proposal about close to 20 years ago now. So we were looking at a higher speed, not true high speed, a higher speed train from downtown Calgary to downtown Edmonton that would operate at 125 miles an hour. And Bombardier built a jet locomotive. So they had a locomotive with a jet engine to power it because at 125 miles an hour, you can't get a diesel engine light enough to power trains at that speed. You need a much lighter engine. The Alberta, and you know, it was going to be expensive. It was going to be a couple of $1 billion by the time it's all said and done. The Alberta government rejected it because it wasn't a true TGV. Now, here's the thing. They wanted a true TGV, which is, you know, 250 miles an hour instead of 125. But the problem was our proposal in the government's, the TGV proposal required a stop in Red Deer. So by the time you get out of Calgary, you accelerate at a rate acceptable to humans and then decelerate to stop at Red Deer and then do that again to Edmonton. The difference in downtown to downtown time with the true TGV was going to be like 20 minutes and it was going to cost in excess of 10 billion. So, you know, was was 20 minutes worth 8 billion extra, but I think I might get a little off here, but I think this was the politicians' way of killing the proposal I worked on. By making it, impossible, basically, economically. Now, on Calgary Banff, I've worked on a little bit of that from time to time. My view is the economics are not going to be there. To double track the line, you're well over $1 billion. And I just don't see them getting enough passengers to make that pay. I worked in our capacity group and worked on, extensions to sidings and double track and all that. And the costs are just unbelievable now. So for instance, one switch with 3 signals, one each for each side of the main line and one for the siding was $1 million. And that's just one switch. Well, you double track, you got probably 50 of them. Plus you got bridges, which can easily go over 100 million without any problem at all. There's a couple of crossings of the Bow, plus a lot of smaller streams. And the environmental remediation, it gets very expensive very fast.
Well, Hyperloop, is that pie in the sky?
I think so. I'm not a physicist by any stretch of the imagination. You guys probably know more about this than I do, but the idea of Hyperloop was you'd have a train running in a vacuum so you don't have any air resistance. But can you imagine keeping the vacuum constantly? The technical challenges of keeping that vacuum are immense in my view, particularly over a long distance.
They're building a test section, right?
I don't know. I thought they'd stop that. Like Elon Musk was behind one of those ideas and he got out of it. And I think maglev is perhaps more practical. And there's at least one maglev in operation in China, and there's several test sections, one in Japan, and somebody mentioned that there's one in Italy as well that I hadn't heard of. So I think maglev might be the difference. And the other thing I would say is you get to the speeds, as you go up the speed range, what you find is you're accelerating and decelerating the whole time. So you're not gaining as much as you think you might, unless you're at a very, very long distance.
Typically, when you stop on Medhurst.
Yeah.
So
A fellow called Medhurst who developed a concept back in Victorian times of England, move people in tunnels.
Yeah.
But it didn't go anywhere because the papers it got into their head that people would suffocate.
Yep.
And it would never test it, but Medhurst thing was not in the paper.
Oh, yeah.
The other thing with it, when folks ask about lubrication, when we look at that phrase, the real McCoy, as I understand it, the real McCoy was how they developed, Eli McCoy, they developed a little boiling system that dropped down onto the rail in the early 1900s.
Yeah, there was some out there. Lubrication, particularly gauge face, has been around a long time. It's I hadn't heard of anything on top of rail prior to about 25 years ago, though.
anything online? Steve?
No, we have no questions online at this point.
Oh, okay. Any other questions? Yeah, it's just a minor one. Now you see the CP trends going on, you often see the Kansas City trends in dispersion.
Yes.
Are those two trends exactly the same in terms of capacity?
Basically, there's only 2 manufacturers of diesel locomotives in North America, General Electric, and what used to be General Motors. It's now CAT owns the other plant. But they will operate interchangeably together. So, and the railroads insist on that because they want maximum interchangeability.
Yeah, backwards compatibility.
Yes.
What about switches and all those things? I come from a place not so long ago in Holland. As soon as that winter spell hits part of maybe only 2 days, but immediately half half a day later, kind of almost a train stop because of the blood switches are snowed in and iced up and so forth. How do we do that again, Campbell?
Well, on the main lines, we typically have propane heaters. So, actually, if you go just out here, at the end of, there's 4 tracks through the city that goes down to 1, you'll see some, remote control switches that the dispatcher controls, and there's big, blowers, that will blow hot air, through the points to melt any snow. And, they can either be automatic or controlled by the dispatcher. That's the most common thing. In branch lines, you can't afford to do that. And usually the section crew goes out with special tools like an ice chisel and special snow brooms and cleans out the points. But that is a continuing problem.
Yes.
British Rail often have a problem in the fall with leaves that get on it.
Yep, that is a problem in North America as well, particularly in the Northeast US. We haven't had as much of a problem here. One of the reasons is in Canada, we have relatively wide right-of-way that you keep the trees back. So the right-of-way typically is 100 feet wide, and you clear any trees within that 100 feet, so you don't get as many leaves. But in the Northeast US, like in Connecticut, they have some very narrow right-of-ways and hardwoods and a lot of leaves in it. That can be a real problem.
Any other questions? Okay, well, Paul, you gave us an absolutely fantastic and fascinating talk, really appreciate it. CPGC has made a donation to Operation Eyesight on your behalf, so it's a certificate that somebody has regained their sight because of your talk time.
Oh, well, thank you.
So much.
Thank you.
So do help yourself to sandwiches and coffee and the bars through there, you probably know. So one thing I wanted to ask is, when you go on coach house, for example, and you look at the LRT, they have to have lights on both sides.
Yes,
Why?
for each track. So
Oh, so if you're going the wrong